Welcome to Introduction to Algebraic Data Types and Recursion Schemes. This video consists of two chapters. The first chapter is notation. We will collect our programming intuitions to define sum type and product type. And through simple observations, we will develop a better notation for function types called exponent types. The second chapter is an application called Recursion Scheme. We will see how recursive structures are defined and how their handling can be generalized. Let's get started. To understand what types are, let's first think about how we construct programs. We'll have a simpler model of a program, where a program is simply one magic box that you put some input and get some output. The program will accept some values, but not the others. As a placeholder for the values which can be put into the program, we will say types. And those magic boxes, we call them functions. Any choice of programming language provides some types as built-in. It can be Boolean types, integer types, floating number types, string types, or spooky void types. They are called primitive data types. We can do a whole lot of things with them, but sometimes they are not enough. That's why almost all programming languages provide you a way of composing new types using the existing ones. They are called composite data types. Essentially, there are only two ways to compose types: having one thing at a time or many things at the same time. For example, when we say IP address, it means either IP version 4 address or IP version 6 address. We mean either of them and not both of them at the same time. We'll call them sum type and write them as addition. On the other hand, IP version 4 address consists of 4 unsigned 8-bit integers. Having multiple things at the same time, we call them product type, and we're going to write them down as product. Those two operations are the only tools that we have in our hands to directly manipulate logical relationships between types. We start from primitive types and populate to the whole program by composing, and the whole program becomes one simple function. Sum types and product types, they form their own algebra. They behave like addition and multiplication in numbers, although they don't have 0, 1, or inverse. To actually handle them as we do with numbers, we have to check 3 properties. Are the operations associative, commutative, or distributive? And yes, they are, and it is quite intuitive. Let's look at the first formula, for example. Having A and B at the same time is equivalent to having B and A at the same time, which is kind of obvious, right? It means they contain the same amount of data, and they are interchangeable, although they might have different formats. So we can say the product operation is commutative. You can easily see other identities are also true, and I will leave it up to you. We have one more thing to think about: a function. After all, what can we do only with the data without a function to transform them? And what programmers call a function, mathematicians, they call them morphisms. We as programmers don't give too much attention if types are sets or not, so I'll just keep saying the word function to keep things familiar. Now we have 3 operations instead of 2: addition, multiplication, and function, from which more rules arise. Let's start with 2 most simplest but crucial observations. Let's say we have a function that accepts a value of type A as input and outputs tuple of 2 values of type X and type Y. We can declare that we will ignore the value of type Y from the output, and now we have a function that maps A to X. In the same manner, we can declare that we will ignore the value of type X from the output, and we will have a function that maps A to Y. Now we have 2 functions instead of 1. Moreover, we can reverse this splitting procedure. Whenever we get an input, we run both functions that we have on the right and compose a tuple of the outputs from the functions. We got back to the function that we started with. We have just proved these 2 representations are interchangeable. Thus, we can conclude that having one function that maps A to tuple of X and Y is equivalent to having 2 functions, one of which maps A to X and the other maps A to Y. This is our first observation. This time, we have a function that accepts input of type A or B and outputs type X. We can declare that we will not take B as an input anymore, and now we have a function that maps type A to type X. We can repeat the same procedure, but this time we will declare that we don't accept input of type A anymore, and we have a function that maps type B and outputs type X. Now we have 2 functions instead of 1. Also, we can reverse this splitting procedure. No matter which A or B we get as an input, we can make X. If we get an input of type A, we can make X using the function above. if we get an input of type b, we can make x using the function below, which means we already have the function a or b to x, and this is the function that we started with. We have just proved these two representations are interchangeable. So we can conclude that having a function that maps a or b to x is equivalent to having two functions, one of which maps a to x and the other maps b to x. This is our second observation. Now let's look at those two observations. The first observation looks like the function distributes over product, a distribution law. The second observation looks just like the first one, except addition is changing to the product. Wait a moment, the operation that changes addition into products. We know only one operation like that. It's exponentiation. Let's replace arrows with exponentiation and see how it looks. Now this looks much more familiar. It looks like these formulas are just exponent rules undercover. It makes sense to declare that the arrows are actually the exponentiation. But to do that, we need to see if the other exponent rules make sense. See, there are three exponent rules involving addition and multiplication. The first one is called power of product, which is the formula above, and the second one is called product of power, which is the formula below. The third one is called power of power. This is the power of power rule. Repeated power is the same as multiplication on the exponent. Let's see how it looks in the function form. This formula can be dubbed as a function that takes both a and b at the same time to return x is equivalent to a function that takes one input at a time, finally to return x. We as programmers can identify this formula as partial application, a closure, or builder pattern. If you're familiar with Gang of 4 design patterns, this formula is more often called currying. Although we didn't formally prove any of those three, we can understand them and make sense of them, and we can conclude that a function actually is just exponentiation undercover. Before we move on, let's look at one more identity that exponentiation should satisfy. We have two identities here. In the world of number fields, the first one is dubbed as however many times you multiply 1, it is always 1. The second formula means multiplying something one time is the same as doing nothing to itself. But we have a problem here, because obviously there seems to be a type called 1. And actually these formulas that we are seeing is more like the definition of 1. Okay, but what can we say about this 1 type? In case of sets, 1 is a singleton set, a set with exactly one unique element in it. And something that is truly unique in our intuition is emptiness. That's why programmers often call one type as nothing type. Programming languages recognize this as a non-type or void type. So the first formula is a function that returns nothing is unique. Let's take a look at the second formula. A function that takes nothing as an input and returns a value of a type is a constructor. We can dub this formula as defining a constructor of a type is equivalent to defining the type itself. Now it is safe to identify functions as exponentiation, and because of that, functions are called exponent types. But why do functions behave like exponents? We can gain some insight from finite sets case. Let's think about a function from set a to set x. To define a function from a to x is to assign an element of x for each element of a. For each element of set A, the number of candidates to be the value of the function is the size of x. We repeat it by the size of a to determine a function. So the number of all possible functions from a to x is x to the power of a. Exponentiation arises naturally in finite sets case, but we can treat them as exponentiation when a and x are infinite sets or when they are not even sets at all. Let's summarize what we've seen so far. We can make composite types from existing types using 3 binary operations. We can have multiple things at a time, we write them as multiplication. We can have one thing at a time, we write them as addition. We can change from one thing to the other, and we write them as exponentiation. And those 3 operations follow the algebra as in numbers that we are familiar with. So we can manipulate types as if they are numbers. And that is why those composite types are called algebraic data types. A perk of having such a notation is we don't have to think about the semantics all the time. we can systematically break down a concept. And as an application, I want to introduce recursion schemes. There is a very rich history involving recursive structure, but we'll have a look at one of the most common interpretations modern programmers have. We will start with the simplest data type with recursive structure, a linked list of integers. We will simply call it list. A list is either empty or not empty, and when it is not empty, there is a value of integer and the rest of the list, which is a list itself. But we can't do that. While defining the list, we cannot refer to it because it is not defined yet. We are in the middle of definition. To avoid this self-reference issue, we will define a function f instead and declare that the list is solution to this equation t equals ft. Note that the function f acts on the type itself, not a value of a type. This kind of functions that acts on types are called higher ordered functions, or functors. So, the solution to this functor equation does not change by applying f. For that reason, we call it a fixed point of f. Many questions can arise. What does it mean to solve this functor equation? Does the solution exist? Is the solution unique? We don't know, but we know that if such type exists that does not change by applying the functor f, it is the type that fully represents the recursive structure of list that we want to define. But as is, this type is rather useless because we don't know how to write a function using it yet. Let's say we are given a value of this type and try to make a return value out of it, say a floating number. This function will have a type t to float. We know that a function is exponentiation, so we can write it in its exponent form. We know that t is a solution to the equation above, so we can substitute by them. We can use the power of product rule, and we are defining a function that maps t to float, so we can substitute t with float. Finally, rewriting this formula in the arrow form, we get the product of two things. The first term is some initial value to start calculation from, and the second term is a binary operator. They are known by the name reduce. By providing those two terms, we can define a function that maps t to a float. Voila! Now we have a function on the recursive structure. This way of building a function from a recursive structure is not restricted to only the list. Let's look at this structure. Instead of one reference to itself, there are two references. This recursive structure is known as binary trees. To make a function from this structure to float, we can go through almost exactly the same steps. But in this case, instead of binary operator, we end up with ternary operator. More generally, when there is a recursive data type t defined as a fixed point of functor f, we can synthesize a function from the type t to another type x by providing a function from fx to x. And this procedure is called catamorphism. Note that fx itself has no recursive structure whatsoever, so we start with a function that has no recursive structure, and we ended up with a function that crushes down the recursive structure into a type x. In that sense, catamorphism is a function that injects the recursive structure into a function. We can even say that we refactor the function from t to x into two parts. The part that is responsible for recursive structures and the part that does actual calculations. In practical applications, naive application of catamorphism usually is not enough, and there is a need to introduce other tools such as memoization or early returns. But we can talk about all those things using the same logic. In general, they are called recursion schemes. Topic of recursion schemes include all the different things that any recursive structures are involved. The recursive structure is not always explicit. A tree structure can be hidden under a list of lists. A list structure can be hidden in function call stacks, and to make this knowledge actually useful, we have to understand the features of programming languages and compilers, and how it runs in the hardware, and somehow beautifully let them interlink together. I hope this talk boosted your appetite for deeper understanding of programming, and thank you for watching.